Okay, so we are now in a position to apply this general lubrication theory to a couple of specific applications that will help us understand both the utility of the lubrication theory and also what the scalings that we derived in the process of the theory actually mean for some physical problems. So let's look at the first application, which is the flow under a slider block. So a sort of generic situation encountered in mechanical devices is where one has to lubricate the relative motion between two surfaces, or two surfaces which are not exactly aligned. So consider, for example, you have a wall of the following form, close to a flat wall. So this bottom wall is perfectly flat. Right, this is y equal to 0. Here we have y is equal to h of x. Right, it's not a function of time. I only have the bottom wall moving, and so because normally what we would have is the top wall moving in the forward direction. But if I transform to a moving reference frame that moves with the top wall, I can then say my bottom wall moves with the velocity u equal to minus u base. Let's say so the bottom wall actually moves in the negative x direction. Right, so what this means is, in terms of my previous problem, I have v equal to 0 and I have u equal to minus ub. So if I make this substitution now, directly I can go to my equation for the pressure. I can substitute u and v here and try to integrate this equation for pressure. Before I do that, I need to specify the form of h of x. So in this simple slider block problem, we'll assume that we actually just have a linearly varying gap width. So h of x, let's say the dimensional h of x, right, can be written as d1 plus d2 minus d1 by L x star. Right, so this gap here is d1. Let's say the gap at the end of my problem is d2. And then d2 minus d1 by L, where L is the length of the overall domain, is my constant slope. If I non-dimensionalize, then I'll get, by dividing throughout by d1, I get h of non-dimensional x is just 1 plus d2 by d1. I take L to minus 1. The L factor goes to give me a non-dimensional x, right, which I can write as 1 plus d21 minus 1 x, where d21 is defined as d2 by d1. Right, and you can see now if d21 is greater than 1, it means that I have basically what it means is that the fluid is moving from the thick region into the thin region. And that's going to be important. If d21 were less than 1, it would reverse the geometry and fluid would be moving from the thin region into the wide region. So that's going to be important for the results that follow. So in this case, we'll consider d21 being greater than 1. So fluid is actually being driven into the narrow part of the gap. Okay, so now we have everything we need to calculate the pressure. So if I substitute this expression, these expressions for u, for v, and for h of x, right, into my equation for pressure, I get the following. So in this case, of course, I forgot to mention that there is no applied pressure gradient, of course. So this motion in this between these two surfaces is just driven by the relative motion of the plates. So there's no applied pressure gradient in this problem. And remember, this was nothing but is equal to v is 0 plus u by 2, so it's just minus ub by 2 times dh dx, where dh dx I can write down immediately here, d21 minus 1. Right? So this is the equation now we need to solve for pressure. Right? If I do one integration, I get h cube by 12 times y, sorry, I'm integrating in x, times x plus a constant c1. Oh, there is one further simplification that we should have done. So you see that when I said g to 0, it means that my velocity scale u characteristic was always left unspecified. So I can choose u characteristic to be minus ub, right? So that u is actually equal to 1. U equal to minus 1 because u characteristic is ub. So the non-dimensional u is minus 1. Which means that here I should have actually had just minus 1. Similarly, here I should just have had minus 1. Alright, so that's just basically, I mean, ub is used to scale velocity. So for simplicity, I mean, it's just, ub is just 1. Okay, so that leaves my equation the same. I can now divide throughout by h cube, right, and get an expression now for dp dx. I'll have 6 here into h by x by h cube plus c1 by h cube. The factor 12 I can absorb into c1, right, because it's some arbitrary constant. So if you want, I could have put c1 by 12 here. Right. And now what is left for us to do is to do another integration. So I can now integrate this directly from x equal to 0, right? I can integrate it from this point x equal to 0 to any position within x. So that allows me to immediately apply one of the boundary conditions. Right, so if I integrate this from x equal to 0 to x, 0 to some x, right, what I will get is P at x minus P at 0, which is just the outlet pressure, right, or P at the basically P outside the region of the slider box. So typically this slider box is going to be something that looks, maybe you have like another portion of the mechanical device extending outward, right? This is the outer region, and then this is the zone I'm interested in, let's say, where the thin gap is present, right? So it's the pressure outside, which might be atmospheric or some other internal gauge pressure. So I just leave it as P out, it's some constant, right? And this must be equal to minus 6 times d21 minus 1. So d21 minus 1 is positive because in our case we're saying d21 is greater than 1. And then I have integration from 0 to some position x, right? And then I have an integration variable s by h cube of s ds plus integral again 0 to x, the constant c1 times 1 upon h cube of s ds. Great. So far this is my equation for pressure. So now what remains is to evaluate these integrals. I of course know what h is in terms of x. It's a known linear function, so I just have to do a couple of straightforward simple integrations. To solve for this integration is trivial. To solve for the first integration, I can use integration by parts by taking the numerator to be 1, second one to be the factor 2, and then using the usual integration by parts formula. Right, so that's a relatively simple exercise. But before that, I can in fact directly obtain the constant C1, right? So I say that P at 1, because I've scaled x by the total length of my thin gap region. I know this is also equal to P out, right? So therefore, what I have really is 0 is equal to minus 6 times d21 minus 1 integral 0 to 1. So now this is a definite integral. Sorry, yes. And then I will leave it to you. So you can evaluate these integrals rather straightforwardly if you just substitute h of x. H of s is simply 1 plus d21 minus 1 into s. It's just a linear function, for which you take the cube. Right? So it's a straightforward integration to carry out. And I will leave you to show that C1 is simply 6 times d21 minus 1 upon d21 plus 1. Okay, we can then substitute C1 back into the equation above to obtain the final pressure. And what you will find, again, I'll leave this as an exercise for you to carry out, is the following. So you get the pressure inside the thin gap is the outer pressure plus 6 times d21 minus 1 upon d21 plus 1 into x minus x squared divided by 1 plus d21 minus 1 into x the whole squared. So this is the distribution of pressure that one obtains inside the thin gap region. So again, this just follows from straightforward calculation of the integrals that we had above. Alright, so now the important thing is to ask ourselves what is the nature of this pressure variation. So if I look at, we can qualitatively easily plot a graph because the expression is quite simple. So if, let's say on top I look at the height variation versus x, right, what I would obtain is, we know that the height actually varies in this manner as a linear function. Right, so if I then look at the pressure, where was I? Yes, so the height of the channel varies in this manner. So now looking at the pressure here, what you see interestingly is this x minus x squared. Remember, x is bounded from 0 to 1. So x minus x squared is always a positive number. And x itself again goes from 0 to 1. This is positive as well. So the largest magnitude that you can expect for the denominator occurs at the outlet, whereas the smallest magnitude occurs at x equal to 0. So where the denominator is smallest, this term becomes the largest. Right? So we expect the pressure to be larger near the thin gap region than towards the outlet where the gap is large. Moreover, the pressure everywhere is going to be greater than P out, or the pressure difference is going to be positive. Right? So if I look at P minus P out, that as a plotted quantity, is going to look something like this. It's going to be something parabolic, but shifted by the x dependency in the numerator in such a way that the pressure difference is greater closer to the inlet. Right. So this is what the pressure difference P minus P out is going to look like, and it's going to be positive throughout. So what you see here is that in the thin gap region between the slider block and the moving plate, you see that actually a positive overpressure develops, and that positive overpressure actually pushes the block away and prevents it or supports it above the flat plate. Now this pressure difference was positive purely because D21 minus 1 was positive. On the other hand, this is of course if D2 is greater than D1, right? But you see, if D2 were less than D1, this term would be negative, and as a consequence the pressure difference would actually be negative and have a slightly different form where it's actually more negative towards the outlet, right? Because again here we would have a negative factor, and the consequence of that would be that the pressure in the gap region would actually be less than the outlet pressure, and that would cause the slider block to get sucked towards the bottom plate. So what this means is if the relative motion of the plates forces fluid into a narrow region, into an ever narrowing region, you actually develop an overpressure that supports the heavy object, or that supports the slider block. On the other hand, if the motion were reversed such that fluid was forced from a thin region into a enlarging region, then you would develop an underpressure and suck the slider block onto the flat surface. So this is an important insight into the working of these kinds of lubricated mechanisms and the lubrication pressure that develops between two surfaces moving with a small clearance. So now that, knowing this pressure distribution, you can always go back and calculate the variation in the velocities. What you would see really is that because there would be a Couette component but also a Poiseuille component because of these pressure variations. And so that's something that you can calculate easily. We just need to calculate dP dx and substitute into the analytical expression you have for u. And then if you calculate du dx, you get dv dy, and then one integration gives you v. Okay, so that brings us to the end of the first application problem. But before we conclude our discussion and understanding our discussion of these long wave approximations, it's useful to consider a second quite instructive and interesting application, which is to study the flow beneath a sedimenting object as it approaches a flat surface. So it's again a problem that fits within the general scheme for which we derived our lubrication equation. So let's look at now application, which is a sedimenting cylinder. So the problem we are considering is, imagine you have a flat bottom wall, right, inside a bigger container, and then in this you have a cylinder, right, which is sedimenting, let's say under gravity or some other force, but let's assume it's gravity. So it's sedimenting under the gravitational force Fg, sedimenting towards a flat wall. And so after some time it's going to move closer and closer to this wall until eventually you have a thin gap region where there's a lubrication layer that kind of counteracts the gravitational force that's pushing this cylinder towards the wall. So if we want to understand how what are the time dynamics of this cylinder as it sediments towards the wall in the late stages of its motion, when there is a thin lubrication region, then we can just focus on that thin lubrication region. So based on understanding so far, we expect that when it almost comes in contact with the wall, large pressures would be developed in the thin liquid thin gap region, right? Because what you're doing is you have to force out fluid from an increasingly narrow region where the viscous stresses that counteract that motion keep growing. So the pressures that you have to develop also keep rising, and that pressure sort of counteracts the falling cylinder and slows down the rate of its sedimentation. But to exactly understand how that time dynamic behaves and what the outcome is, we need to do a calculation. But the beauty of the problem is, of course, we don't have to solve for the flow all around the cylinder, and we don't have to worry about the nature of the container walls and so on. Rather, the result is going to be independent of those aspects purely because of the thin gap lubrication region and the high pressures that develop there. So if I now look at the if I can just look at the thin gap region, then I can set up my problem. So zooming in, what we really have is a flat wall, right, and then a portion of the two-dimensional cylinder. Right, let's say the portion closest to the wall, right, has a gap b, which is a function of time, right, and then my thin gap region itself extends. So the extension now is not very clear, but it extends over some region where you can use the thin gap approximation. If you go further and further away from the narrowest point, you will ultimately go into the outer zone where the thin gap approximations fail. So where exactly to apply what exactly the domain for the thin region is not very clear, but as you will see, those details don't really matter, and it's even something that you can keep adjusting as the cylinder approaches closer to the wall. Now once again, remember that we are working only in 2D, so this is a cylinder approaching a plate, but at the end I shall comment on the small differences that arise if you take a sphere approaching a plate. There you would have to look at a 3D full problem, or the lubrication problem would be the lubrication equations would be in 2 dimensions, whereas right now our lubrication equation accounts only for variations in 1 dimension. Alright, so this is sort of our domain where the end boundaries are kind of fuzzy and evolving, but typically we expect the length scale over which we are going to consider the thin gap to be L, and then we have the gap between the plates, of course, is a function of time, but at any time we can take a typical length scale to be B naught. Right? B naught in fact could be the value of B naught is the value of B at t equal to 0. Right? And we can use that as our sort of length scale for setting up the problem. So the first step here is we could start from the beginning and derive the equations, but we already have our lubrication equations. So what we need to do is to identify what the different terms are. So in this case, the bottom plate is not moving, so U is just 0. The top plate in this case does move, right, and it in fact moves with the sedimenting velocity. So it's if B of t, if B gives you the function of the bottommost position, because the entire thing is a solid, we know that the velocity v is just b dot, right, the rate of settling of the sphere, which is also just dh dt. What we now have to do, of course, is to specify what h is. Now let's say that our sphere, right, has a radius of capital R, right, so R is going to be much larger than B. At the same time, the length L that we take, although it has to be larger than B, it should be smaller than R, because we can't expect the lubrication layer to extend all the way to R, because if we go up to R, we are certainly inside the outer zone. So we have a separation of length scales where B is much less than L, but that itself is much less than R. So with this understanding, we can actually approximate the shape of the cylinder although its exact shape is more complex, we expect that in the thin gap region we can approximate it as parabolic up to second order in L by R. Right, and so we can write in fact that h of x comma t in our problem is nothing but b of t plus, if you work out the exact geometric factors, it becomes radius by 2 times x square by radius square plus order of x to the power 4 by radius to the power 4. So because x by r we are going to consider in a domain where x by r is small, because remember I said L is much less than r and L is the maximum value for x. So then we can drop these terms off, and this is what gives us the parabolic relationship. And now if we scale this throughout by b naught, right, so these are all dimensional quantities, of course. Right, so if I scale throughout by b naught, but I scale x by L, what I'll finally get is h is equal to scaled b I'll have x square, but I would then have to account for I will throw out a factor of L square, and then I had the factor of R square sitting here, but I can cancel those terms off. So finally what I get is just b plus L square by 2R b naught times x square. And so I can write this in general as h is equal to b plus alpha x square, where I know for the application of the thin gap theory alpha must be less than 1, or alpha must be a small number, which means that L square by 2R b naught, dimensionally speaking, must be less than 1. Now the important thing here is what guarantees alpha is small is the fact that the choice of L is really up to me, right? So R is the radius of the sphere, b naught is determined by when I start studying the problem, but that at any given time where my initial condition is b naught, I get to choose the domain length L, which defines the region of the thin gap zone. So really this condition is what helps me identify what should be the length of that thin gap zone. So I should choose L, the length of my thin gap zone, such that this factor is small. So if L is made too large, right, then such that this factor starts becoming order 1, it means I have already entered into the outer region, because then the variation of h along x is not going to be of long wavelength relative to b naught. Alright, so this is now our h of x comma t, right, keeping in mind that alpha is a small number. So I can then go and write down my lubrication equations. Right, so applying the thin gap pressure equation. So before we continue, remember what our objective here is to ultimately understand the rate of settling of this cylinder. So I know that the motion of the cylinder is governed by the balance of forces. One is the gravitational force, the other is its own inertia, and the third is of course the viscous stresses and the pressure forces exerted by the fluid. But if we consider that we are in a Stokes flow regime, so that the cylinder is sufficiently small, then so that we can set Reynolds equal to 0 and the Stokes numbers are small, then we can neglect inertial effects. So the only balance is now between gravitational forces and the forces due to viscous stresses and pressure forces. Once again, remember that the pressure forces in the thin gap region, however, are 1 by epsilon times larger than either the outer pressure forces and then the viscous stresses themselves. So therefore, if I want to calculate the total force exerted by the fluid on the cylinder, to leading order it suffices to simply calculate the force exerted by the pressure in the thin gap region on the cylinder. We can even neglect the viscous stresses exerted on the cylinder because they are going to be in order epsilon smaller than the pressure force. Right, this follows naturally from the fact that the characteristic pressures are 1 by epsilon, whereas the characteristic largest viscous stresses are order 1. So therefore it becomes important to calculate the pressure in the thin gap region, and if we know the pressure in that thin gap region, we can get a leading order approximation to the force exerted by the fluid on the sedimenting cylinder.